Hi there, today we're looking at movement pruning, adaptive sparsity by fine-tuning by Victor Sun, Thomas Wolf, and Alexander M. Rush of Hugging Face and Cornell University. On a high level, this paper proposes that you should, if you have a transfer learning objective and you want to do pruning, you should not do pruning by weight magnitude, you should do pruning by how much the weights move during the transfer learning. This yields better result in the very sparse model regimes and is specifically relevant to current NLP transfer learning tasks such as BERT models. So if you like content like this, consider subscribing and sharing it to your friends, and as always, leave a comment if you have anything to say on this. All right, let's dive in. So they say magnitude pruning is a widely used strategy for reducing model size in pure supervised learning. So what is magnitude pruning? Now, if I have a neural network, let's say I have a convolutional neural network, and I input my little cat right here, and I have a bunch of layers, right? And now if we look at these layers, each of these layers is going to be made up of these units of the neurons, and the next layer is also made up of these neurons. Now, what kind of neural network that is not that important, but what is important is that you have these connections from neuron to neuron. And in, let's say, a fully connected network, every neuron is connected to every other neuron. In a CNN, that would be slightly different, but in essence, you have a lot of connections here. And these are usually called weights. So these are the weights. Now, the problem is, if I train like these giant neural networks and I want to ship them, for example, to mobile devices, to my customers, then they won't be able to download gigabytes of models or even like hundreds of megabytes of models. It's just not possible. So what we want to do is we want to prune this model, which means we want to remove parts of these weights, a lot of these weights, but we don't want to lose accuracy of the network. So imagine I have a network and that's trained. It's an image classifier. It's here, it's cats or dogs. And I have it trained to a good accuracy. I want to delete these weights, but I want to retain the performance. And these methods are called pruning. Now, what people do is usually they sort of go in a stepwise fashion. They say, well, first of all, I don't need some of these, and then they delete some, and then they sort of retrain the prune network. And after that, they go again and they say, well, I don't really need that one, and I don't really need that one. So they do it in this stepwise fashion until the network is of the size that they want. And the hope is that you don't lose too much accuracy. So the question is, how do you select which weights you need and which ones you don't need? And usually this is done by so-called magnitude pruning, which means that you look at the weights, and the weights, they'll have some distribution. There'll be very negative. So here is very negative weights, and here is very large positive weights. And what you'll say is that, okay, probably the weights that are very large, they contribute a lot to the signal of the network, within the network. And the weights that are quite small, they're, since there's all this noise and stuff, they're probably not that important. So I'm going to cut off, basically, right here. And everything that's in here, I'm going to delete. Those are the non-important weights, whereas on the outside, those are the important weights. This is called magnitude pruning because it goes by the magnitude of the weight, the absolute value of the weight. So you don't actually need, so there's not one threshold here. You don't need a threshold. You simply need a method to order the weights, right? And then you keep removing them until you're satisfied with the size. So this is magnitude pruning. Now, what's the problem with the magnitude pruning in these kinds of tasks? They say, however, it is less effective in the transfer learning regime that has become standard for state-of-the-art natural language processing applications. So what do you do in these transfer learning regimes? In the transfer learning regime, and actually, let's go with the image example right here. Even though it's mostly used in NLP, we can do the same thing. So let's say we have a classifier here for cats and dogs, our classifier. And we had a big database of cats and dogs images, right? So we were able to train that fairly well. And we don't prune it yet. We have this full network. Now we want to adapt this to a task where we want to recognize whether or not the animal is sick. So we developed this app for a veterinarian, and it's like a short screening for a particular disease that a cat might have. And we already have this cats and dogs classifier, so it's reasonable to assume that this classifier has some good features to work with cat and dog images. So what we can do, instead of, because let's assume for this other task, we just have this tiny little data set, which is not enough to train a neural network of this size, right? But so in the first step, we'll train this big neural network on the cats versus dogs, and then what we do is we transfer learn it. So we transfer all the weights right here, and here we have a different task now, sick or not sick, right? This is cat, this is dog, and here is sick or not sick. Not sick. And of course we can't transfer these particular weights, but we hope that the features here will sort of be the same. So we transfer them, and then we train these weights, including the head right here, this part, we train it on this little data set. And we hope that we already have this good starting point. We only need to, learn basically the specifics of what makes these two data sets different, and we won't have to learn the entire task of dealing with cat and dog images from the get-go. Okay, so this is called transfer learning. Now, in this case, we combine the two. So first, we want to transfer learn, like if we build this app for vets, and then we might say, oh, this is not only for vets, this is actually for anyone who has a cat or a dog at home. So what we could do is build an app where anyone at home could scan their cat, and it would output like a probability of the cat having that disease. So we want this neural network is still the same size as this neural network. So now we want to do the pruning. We want this neural network to become sparse, to only have a couple of connections left such that it's a few kilobytes large, right? But retain performance. Now they say when you do this step, you can't just do the magnitude pruning like you did right here. And why not? Because this model right here is not the result of a training step, like of a regular training process, but is the result of a transfer learning process, where first you do the big training and then second you adapt it. And why is that the case? Well, ultimately, what you want to do is you want to prove the non-important weights. Now, there could be a weight right here, this one, that is very important for the cat versus dog task, but that is not important for the sick versus non-sick task. And we know that in these transfer learning settings, the weights, they don't tend to move that much. In general, the research shows that once you've trained a neural network, basically the beginning is important, but then once you did it, like if you adapt it or transfer learn it and so on, the weights, they won't move that much. So in essence, this weight maybe starts out right here, and it will sort of stay around this place. It will maybe go a little bit down because it's not important, but it won't move much during transfer learning. That's just a property of transfer learning. So this paper here says we can't just use magnitude pruning when we transfer learn, because what we'll basically say is we'll assign the importance based on the original neural network task on the cat versus dog. We will misspecify the importance of the weights. What we should do is actually measure the importance with respect to this task. And how do they achieve it? So on a high level, they're basically saying, okay, if we start out, well, this was fatal. If we start out with a point over here, let's make that red. I want the color red. Well, it's blue now. So if we start out with a point over here, what we should do is we should observe how it moves during transfer learning. If it moves towards 0, then it's probably not that important for the new task. And if it moves to be even larger, then it's probably important for that new task. Okay, so that's a high level. Now, how do you measure how it moves, and how exactly do you do all of this during training such that you don't make mistakes? That's the point of this paper. They say, we propose movement pruning, a simple deterministic first order weight pruning method that is more adaptive to pre-trained model fine-tuning. We give mathematical foundations to the method and compare it to existing zeroth and first order pruning methods. Okay, so we said, so that's basically on a high level. That's that. Now, how do they actually do it? What they do right here is the following. They say what we can define each network layer basically as a matrix multiplication by a weight. Now, you can express pretty much any neural network as such a multiplication with a weight. So you have x, the signal in each layer, and you multiply that by the weight matrix w. Now, if you prune the neural network, you can see that right here. What you're saying is, basically in here I have the matrix M, which is a mask. So the mask is either 0 or 1 for if a weight is active or if a weight is not active. Now, this is not a matrix multiply, actually this is like a Hadamard product. But you have this mask matrix. And what decides on this mask? This mask is decided, as you can see right here, by this S. So S is a matrix that for each entry in W, it will decide how important it is. Now, in the classic sense, in the magnitude pruning, you already saw that this is just going to be the absolute value of Wij. Okay, and then the top V simply means that you take whoever are the most important, the most magnitude, that those are going to be 1 in the mask, and everything else is going to be 0 in the mask. Okay, that's how the W determines the S, and the S determines the M. Okay, so what you ultimately use is the M right here. But now what we want to do is we want to actually make the S based on the movement. And the movement is not really a defined concept because it goes over steps and so on. So how do you do the movement in a kind of dynamic way? And this paper says you should do it by gradient. So you should observe the gradient of your loss function with respect to this S matrix, to this importance matrix. Right? What does it mean? So what does it mean? It means let's consider this quantity right here. If S is the importance of a particular connection, and if the gradient is large, that means this connection moves a lot, right? Like the loss pulls it into a particular direction. Okay, so we're not talking about yet which direction. Actually, the gradient has a sign. It's either positive or negative, right? So by this quantity, you can decide how much does this new task want this particular importance score to move. So this is a direct measure of how much basically the loss function pulls on that importance score. How much, and now you can simply decide if, and they have these, I think they have a diagram. Yes, so, but I don't like that. Let's go, so we have right here, we have what's the value of this gradient of L with respect to S, and here is W. So if the gradient is positive and W is already positive, that means the gradient goes into the positive direction. So you increase the loss function in that. Let's put the negative gradient here, because you do gradient descent, right? So So if the negative gradient is positive and the weight is already positive in this case, that means the weight is already high, but now the loss function wants to push it even higher. So that must be a very, very important weight, right? Like it's like very good. The same goes if the gradient, the negative gradient, is negative and the weight is already negative. The weight being negative already means the weight, it has a negative sign, and then the gradient wants it to go even more negative. Right? The optimization procedure says this thing should become even more negative, and also we say, that's probably a good weight. Now, the other two cases means basically the weight's already positive, but the gradient wants it to go negative, which means it's pulled towards zero. Now, it's entirely possible that it's going to cross zero and going, like if you're here, going from over here, going to here, cross zero and become like super large. But that violates our basic assumptions that the transfer learning doesn't move the weights too much, right? What you're caring for is basically this local neighborhood right here. Okay, so you can make the fair assumption that these weights are not that important in the case where the negative gradient goes against the sign of the weight. So this is of course discrete right now, but we can actually assign a number by how large the gradient is and by how large the weight already is, and therefore we can make a score. So the importance score right here, as you can see, is the weight multiplied by the gradient of the weight. And they can actually show mathematically that if you do this over multiple steps, so you optimize while you do this pruning, and they do some sort of a soft pruning, so you can kind of correct your mistakes later on. I mean, they have hard and soft pruning, but in any case, they can correct their mistakes later on. This will actually result in these importance scores being an accumulation over the training, over the entire training of this quantity. And that's pretty cool, because that means eventually you'll sort of have a consistent estimator of these importance scores across your training procedure. Okay, because the main fear with something like this, of course, is that it's very brittle and very much depends on the training dynamics, and who knows if in step one something bad happens and so on. But the math behind this here gives sort of more evidence that it can be like a self-correcting mechanism and is actually not too dependent on the particular training dynamics. So they do this experimental setup. Now they have some quirks here. Actually, let's first go to the actual different methods. They compare different methods right here, where they say, okay, there's magnitude pruning. It's a zeroth order, which basically just means you just look at the weight magnitude. That's it. It's top V, which means you just pick the top whatever, and the objective is just the loss, and the scores are just the absolute value. We've seen this. Now, movement pruning, on the other hand, is first order, which means you look at the movement, in our case, the gradient. As you can see here, those are the importance scores. And you use this straight through estimator, which is basically just a way of saying that even though you're masking some things in the forward step, you shouldn't mask them in the gradient backward step, because you still want gradient signal to reach. So if you have layers and you have a weight right here, at least that's how I understand it. I have not read that paper. But if you mask this one here, you still want the gradient to sort of flow backwards, because you still need the actual importance scores for the weights that here below connect to this weight. I think that's what is meant. Not entirely sure on this though. But you can see that the objective function is also the actual loss function. Now, this is contrasted to a baseline called L0 regularization, which is quite similar, but is also first order, but has this sort of regularizer right here and uses the Gumbel softmax in order to determine the scores. And as you can see, it also has a different score function, and it has this continuous hard concrete importance masking function. And they have a variant of movement pruning that tends to perform a little bit better, which is soft movement pruning, where instead of just going by the loss function, optimizing the loss function, they optimize the loss function plus something. Now they have, as you can see here, they have a thresholding masking function. And the threshold is actually dynamic, or it's determined by the importance scores, and they have then a regularizer that make the importance scores sparse. So instead of saying we just want the top 5% of weights, they now just put a lot of mass on this lambda right here, which will cause the S to be sparse. And they if they are not happy with how many weights they prune, they simply increase or decrease this lambda such that they get to their desired sparsity. Of course, you see there's the direct trade-off with the loss function, right? So the more you put weight on this lambda, the less weight is you put basically on the loss function itself. So you have the trade-off here is very explicit, whereas in basic movement pruning, it's just given by you masking away completely the bottom 1 minus v of percent of the weights. But you see the score function is the same. Oh well. The score function here, the score function is the same. Okay. Now there are quite a number of tricks here, like there's this sparsity scheduling function and so on. So as always in NLP and with any big models, there are a bunch of engineering tricks that make everything work better. And you can never exactly tell how much is due to that and how much is due to the actual technique. But if you can sort of assess whether or not these it's done well. And this here, actually, the rationale makes sense, and that's why I tend to think that it is actually a better method. And the experiments are very, very convincing, let's say. Okay, this is just a pictorial comparison where you can see movement pruning, magnitude pruning. All it does is it looks at, after you fine tune, what are the weights, and it just cuts away everything in the middle. Doesn't care about how the weights were before. However, movement pruning looks at the combination of what were the weights before and what are the weights now, and it cuts away everything where the weights moved towards zero, which are these quadrants right here, and it leaves in everything where it moved away from zero. Or that's the ordering, let's say, that how much it moved. Okay, experiments. Now, as you might already have figured out by now in the machine learning and especially the NLP community, the methods presented always outperform the previous methods. In this case, it's pretty special. So they test this on these number of tasks, quad, NLMI, and QQP, and these are quite hard tasks from an NLP perspective. Like squad is question answering, MNLI is like language inference. So these would be on the, I would guess these are on the, for an NLP system, on the harder side of tasks. So it's fairly cool. And as you can see here, now just focus on, first of all, focus on this MAP, which is the magnitude pruning. So that's the baseline, if you will. And the purple one, the SMVP, which is the soft movement pruning. Okay, now you can also focus on the MVP right here, but they're approximately the same. Now the RPP, you can maybe see in the graph, is performing fairly well, even compared to the full model. It's another baseline basically, but we just want to compare those two, and you can see that in this regime that the magnitude pruning outperforms the movement pruning. But however, in this regime, the movement pruning is much better, and that's the percent where the percent of remaining weights is very, very low. So this is kind of the extreme sparse case where you only have 10% or you only have 3% of the weights left. And you can see that the movement pruning is outperforming the magnitude pruning by a lot. Okay. Now they do discover that so this happens in all of these tasks, as you can see right here, and they do discover that if you then distill the model further, so in distillation, this is yet another technique that you can use to boost the performance of the transfer learned model. So in distillation, you would not only train the model on you. So you have this model that you transfer learn, and you have the pruned version. And in the pruned version, what you would do is you would simply also train it on this data set. But what you can also do is you can distill this model right here, the one that you trained on the same task, right? That's presumably better because it still has all the weights, okay? You can run a data point through both. So the same data point goes through this, and you get an output, which are logits, which is like representing a distribution saying, yeah, it's about this high. Now, instead of assigning the hard labels, so here you also get the label, right? It's a supervised learning task like 1 and 0. You also put the data point through this model right here, obtain whatever that model would have said, and let's say it's about this. And now presumably this model is better already. So you say, well, the label here says that it's this class, but the model that's really good says you shouldn't be too sure about it. So you can sort of mix the two losses. And this process of transferring the knowledge of this model to here is called distillation, with the lower model being the teacher model. Now, if you do distillation, you can actually improve your performance even more, and they show that in the experiments here, especially again in the low parameter regime. But you can see, for example, in squad here, that the distilled movement pruned method now catches up with the magnitude pruned method in the not so sparse regime. Okay, and they analyze these weights, and as you can see, that expected, the magnitude pruned method, it will simply cut out anything right here. Right? That's not a surprise. Whereas the movement pruned method, it will leave a lot of these weights alive. So as you can see, basically, it's very much the case, since you can outperform the yellow one can outperform the red one. It is almost warranted to say that this magnitude pruning wasn't the best choice. It's actually a better choice to leave some of those weights in and actually cut some of the weights that are large out, just based on their movement. Now the V here in the middle is of course due to the fact that if a weight is here, it was probably not super important in the first place, and since this thing removes anything that moves towards 0, any points starting, let's say, around here, moving towards 0 would end up here. So all the points that end up in this region probably moved toward 0 during training, and therefore are cut away. So there's not just, like, for there to be points, there would have been points that started even more in the middle and then moved out to here, right? And there's just not as many. So that's why you have the V shape is very natural to expect right here. So they analyze this then in terms of where the model cuts the weights out. Now they experiment on a BERT base thing, which is a transformer with 12 layers. And if you don't know what BERT is, you can go look at my video on BERT, but you can see that the magnitude pruning will sort of cut all the weights in the layers equally. So it will sort of go through the layers and take away, let's say, 90% of each. Here you can see 10% of weights remaining. Whereas the movement pruning, especially the soft movement pruning, will actually make a large difference. It will remove much more of the later layers weights and keep the lower layer weights, which I think if you do transfer learning from these language models, it tends to be that the lower layers maybe pick up, if you think of a CNN, the lower layers might pick up, on these essential image features like corners and so on, and the higher layers will pick up on the task-specific things. Now, if you do like a big pre-training tasks, you might have a lot of information that you need there, but then if you distill it and transfer it down to like a small task, where only a single thing is important, like in squad, it's only important what's the answer to the question, then you can probably remove a lot of that superfluous information that was there, like high-level features from the pre-training task. I mean, that's my guess here, but they also have explained that. So yeah, that was this paper. If you're still here and you enjoyed it, leave a like, tell me in the comments what you think, and I'll see you next time. Bye-bye.